Let's begin. No quiz today. Okay? No quiz today. Okay. Now, in the interest of graphing bars, like where we finished off last time, we did this simple little example of type of housing versus number of students. I was looking at your quiz answers for the open-ended question, for the free question on the last quiz about what historical figure you'd like to have dinner with. So I want to share with you the answers. I was laughing so much, and I'm very proud of all of you. So some very inspiring suggestions. So here's the list alphabetically. We got plenty of political figures for the foundation of America. Like that's very important to me as an immigrant, like personally learning, you know, Hamilton, Lincoln, these guys. There's Jesus, obviously there. Einstein, Bohr, Niels Bohr, Beethoven, Ariana Grande. Okay, so there's Hitler. Okay, now before you jump to any conclusions, okay, we don't have a Hitler supporter in the class. It's like, because why did they want to have dinner with Hitler? You know, because they want to get into their mind and how sick he was. Anyway, so, but apparently I think there are three who had a death wish. One who wants to meet with Hitler, one with O.J. Simpson, and the other one with Hannibal. So, you know, make sure you get salt on the menu. But now, the Hannibal story is funny because as I was doing my PhD in Tennessee, one of my very good friends who was doing his PhD as well, very interested in literature, and you know, one year we would like focus on one author, read Dostoevsky or Tolstoy, and one year he wanted to read the Hannibal Lecter novels, and he disappeared. Like he would like be like, "Hey guys, I'm going to read," and he got really immersed in the novels. And you know, 3 months into it, we were sitting at dinner, and he was talking to me, and he started telling me a compelling reason for why Hannibal Lecter was eating people, and I'm like, dude, like he's like, but you know, I can understand why he's doing this. So at the time, this was around 2006, there was a new website that sells funny T-shirts. It's called shirt.woot.com. I don't know if you're familiar with that. If you want cool T-shirts, just go on shirt.woot.com. They were purchased by Amazon, but at the time it was established in 2004, so I knew of it right at the beginning. So they would set out this competition among artists, like give us some designs and we will print it as a T-shirt and sell it from your design. And so it just so happened that day, this T-shirt showed up on the website, and he was watching, so I bought it for him, and I came to him one day. He was like, "This is was a funny inside joke, you know, but the Hannibal Lecter, you know, rabbit." Anyway, okay, so nobody laughed. Poor taste in joke. Okay, now how can we tie this back into statistics? I have all of these data. All right, obviously they are nominal, right? It's just nominal data, no numbers. I cannot put them in categories. Can I? Can we put them in categories? Sure. What categories can we put them in? Bad people versus good people. Sure. Pardon me? Dead or alive. What else? Historical figure. Okay.
Time frame they're born in.
Okay, that could be, but you know, this is spanning, yeah, maybe well, Jesus is going to be an outlier, right? So how about we put them into, so we combine somewhat your answers, like historical figures, literary figures, contemporary figures, right? And outlier, other, right? So I came up with these categories, historical figures, cultural icons, scientific minds, and entertainment, creative figures, and other, right? And then I did a bar chart, okay, to summarize what you all have described. And look at this. This tells me so much about your answers than a long table like that, right? The power of descriptive statistics. So I know 6 of you picked scientific minds. 8 of you are going to be maybe the next president, possibly one of you, historical icons. Visionaries like Martin Luther King, right? So there's about 4 of you. Entertainment, Ariana Grande. You know, cultural icons, other. This is where Hitler fits in. No, actually, I put him here, but other, I think, something that doesn't fit in a historical figure. In creative and literary figures, there's a few. So what this tells me is that there's a yearning for knowledge about our history, and you guys are quite well cultured. You know, a lot of answers were about literature and literary arts. Okay, and I also could do a pie chart with this information. So 18% of you picked scientific minds, 24% historical icons, 12% visionaries, and so on. Okay, it was good to tie this back into statistics, right? All right, so we left off with bar charts last time, and we're gonna use the same data next on that same spreadsheet if you wanna pull it out, and we're gonna do a Pareto chart. Now, a Pareto chart is simply a type of graph, like a bar graph. However, the data, the bars are listed in descending order, so that you put the top category at the beginning, the one below it, the one less than that below it, and so on, all the way to the smallest category. So what you need to do in that case is very simply sort the data and then do a bar graph, okay? Typically, Pareto charts are done horizontally, so you read them from top to bottom. Visually, they're more appealing like this. So this is the data that we will be dealing with. Let's swap to, what is it, bar chart, Pareto. Okay, let's go to our spreadsheet. Move it to Creston. Sorry, I'm gonna have to turn my back to you again. Okay, so we did this last time, the bar chart. Let's do the Pareto chart today. Some of the other charts, so go here, Pareto chart. Let me fit the slide a little bit, just do it to 100% or maybe 150. All right, so there's 2 things going on here. There's a class and a number of fundraiser items sold. So there's Mrs. Carter's class, some just random names. And number of items sold, they're not sorted. So if you were to go and do a bar chart here, it's not gonna be sorted, it's gonna be put randomly either by the list, the category list that you chose over here in this order. What you want to do is really sort this in descending order. Now, you could do this by going here and say sort sheet Z to A. Now, when you do this, Google Sheets is smart. It retains the first row as the header. It doesn't sort it with them. It instead sorts these guys, but also updates this column so that it matches this sorting. And now when you have this sorting, you can just simply go and do a bar chart, a horizontal bar chart. So you select all of these guys and then insert chart. Again, it's gonna try to do that thing. Okay, so I'm gonna go here and just pick this horizontal chart. And now this is called a Pareto chart. It's just a bar chart that is sorted and going from top to bottom. So now you can quickly and easily read it. Say, oh, Mrs. Boyd's class sold the most items for the fundraiser. Next came Mrs. Carter's, and so on and so forth. So if the data is sorted, if the bar chart is listed in descending order and it's top down, it's called a Pareto chart. That's it. It's nothing more than a bar chart. Okay? All right. Let's resume. A side-by-side bar chart and a stacked bar chart. So there are a few more bar charts. They're very popular in statistics. The side-by-side bar chart is a type of bar graph where you have 2 or more categories that you want to compare to each other. Like, housing choice for sophomores and juniors, for example. How many sophomores prefer apartments and how many juniors prefer apartments? How many sophomores prefer university housing versus how many juniors? So 2 categories or more, you could have 3, 4, whatever, right? And you put the bars next to each other. Okay, so they're side by side. Or instead of putting them side by side, you can stack them on top of each other. There are advantages to each one of those graphs. The stacked bar graph typically will give you the relative size proportion in terms of like thinking of which category is bigger than the other. Okay, so let's go ahead and do this with the following data. Again, this data is in this spreadsheet. The question is to create a side-by-side bar graph for the following data describing the distribution of housing types for two different samples of students. All right, and then asks you to make a conclusion about the data. We'll get to that in a second. Type of housing, we have apartment, dorm, house, and a sorority or fraternity house. Number of freshman students, we have 13 in apartment, 24 in dorm, and so on. And then number of sophomore students, 20, 15, 9, etc. So you can see you have two samples, two populations, or two samples, different samples from different populations, right? The sophomores, the freshmen, right? And you want to compare the two side by side. Okay, let's go ahead and do this. So side by side bar chart, and I have the data already set for you over here. Now, as long as you have the categories correctly set up for apartment, we have 13 freshmen, 20 sophomores, and so on. Google Charts, Google Sheets will take care of it, of the chart for you. You just simply do the selection of the table, then insert chart. Of course, it always defaults to a pie chart. And then you just check this column chart, and look how cool this is. It automatically colored it and picked it and even put the labels for you and everything. A nice, good-looking chart that is clear and self-explanatory, right? And what this tells us that for apartment, so red is sophomore and blue is freshman. So for apartment, sophomore students generally prefer living in an apartment, but for dorms, the freshman students prefer dorms more. So, you know, by a little bit more, you gotta measure this. So we have 15 students in the dorm from 15 sophomores in the dorm. You got about 10 more, almost 10 more in terms of freshmen, right? For house and sorority, it also flips, but it's just about the same within, I would say, like these differences here are insignificant for these two categories, okay? Are we all synchronized? Good, excellent. All right. Okay. Now, the stacked graph is the same thing. However, it tells you a little bit, it tells the story a little bit differently. And it might shed some more insight. So we're going to take the same data and go to the stacked graph. But instead this time, so this is the same data. Instead of doing the side-by-side chart, you're going to do a stacked chart. Again, you go pie chart. And you see here the stacked charts. You can do them vertically or horizontally. I like to do them vertically for these cases. Okay, so now when you do them vertically, it shows you the relative proportion, okay? It shows you kind of like in terms of relative size, like how big the proportions are for the preference between the students. I mean, you can tell that from the side-by-side bar graph. Okay, now notice the size of this one. Okay, so these are the freshman students in blue, number of students freshmen. So you have 13 in apartment, and then you have 20. So the size of this red one is 20. Not the total thing is 20. This is 20 students, okay? And then you have 13 students below it, and so on and so forth, okay? So in other words, the height of this bar is the sum of all students who do apartments. The blue are the freshmen and the red are the sophomores. So in a way, this is giving you the proportion, the relative proportion out of all the students. So it can shed more insight into which category is bigger. You don't have to, and how much bigger it is, okay? All right, so bar graphs are cool. They're important and useful. It's easier to see that more students overall live in dorms than in apartments. Yeah, so the other advantage of the stacked graph is that it gives you also the total population per category. So we know overall of all students, more students prefer dorms. Not that much, but for this sample, more students prefer dorms than apartments and then house and sorority. Because that's the other advantage of the stacked bar graph. Okay, finally, we hit the histogram. So we did bar graphs on kind of all of these arbitrary data. But one of the key things that is very interesting for statistics, very important for statistics, are these frequency distributions. And we didn't plot them yet. We talked about them last time. But the next step is to actually plot a frequency distribution. And that will be the most essential piece of continuous or big data statistics that we will do, is looking at those frequency distributions. So plotting a frequency distribution is no different than making a bar chart for the frequency distribution. However, when you do it for a frequency distribution, a few things change in that the bars, the columns, are going to be adjacent to each other. If you look at the previous graphs we did, notice these bars belong to distinct categories. I could put house over here, dorm over there. There's no adjacency. I can put this here, this bar here, and the other bar over there. There's no continuity on the x-axis, okay? Because these are nominal data, categorical data, right? So that's just a general bar graph. But when you apply this technique of the bar graph on a frequency distribution, remember the frequency distribution on the x-axis, it has a bin size, 50,000 to 54, 999, and then 55 to 59, 999, and so on and so forth, right? Those are continuous bins. They are continuous categories. So the bars for a frequency distribution are going to be adjacent to each other. Now, the size of the bars, how tall they are, is going to be the count, just like here. But they're going to be adjacent to each other, very close. Not overlapping, but they're going to be just touching each other, very close to each other. In that case, we don't call them a bar chart anymore. We refer to those as a histogram. So a histogram is a bar chart for a frequency distribution, specifically. A bar chart is a bar chart, but when you apply it to a frequency distribution, you start calling it histogram. Okay? So, some historical snippet. It comes from the words histos and gramma. Histos means anything that stands upright, and gramma means chart. So a chart that stands upright, it could be called for, a bar graph as well. Was coined by this guy called Carl Pearson, a mathematician, in just as recently as 1891, not that long ago, when he did his lectures at the University College in London. Okay, cool. All right. So for frequency distributions, you could proceed by doing your bins like this and doing the count and then going and trying to plot this. The challenge, though, here is what is your x-axis going to look like, right? What do you put? What number do you put on the x-axis? 80,000, 84,000? Or can you edit the chart so you can put 80 to 84,000? So we're not going to do it this way. There's a built-in function in Excel, in Google Sheets, in Python, in MATLAB, in every spreadsheet software, every software that just takes a set of data and does the histogram for you in one shot. Okay, but it's going to need some tweaking a little bit. So I will introduce you to that function right now. Just the same way we did frequency, we're going to do something called histogram. Okay, so let's see. Where is it? Okay. Now, there are pros and cons to this approach that I'm going to describe because you don't have a lot of control over the histogram when you do it. Some tools will allow you to have control. So for example, I would like to have control over the first bin, the lower limit of the first bin. All of these histogram functions in Excel and Google Sheets, they'll give you the option to choose the number of bins, the number of classes, 6 bins, 7 bins, whatever, right? But they could choose an arbitrary starting point, usually the lowest value in the data. So let's see how this works. If I were to select just this guy here, this first column. So this is the data of the salaries. It's not sorted either, right? So notice 50, 62, 67, then 53, 63. It's not sorted at all. Now, if I go insert chart, same thing in Excel applies. Okay, it actually figured out that it wants to do a histogram for me. Okay, maybe because I did it before coming to class. All right, let's see. So try to do it when it automatically picked up a histogram. Okay, it's pretty smart because it saw a one-dimensional array. What is the bin distribution that you have? It starts at 50,000. Okay, all right, very good. So now, is this consistent with what we want? So we have 1, 2, 3, 4, 5 bins over here, right? But what I wanted is, we wanted 1, 2, 3, 4, 5, 6, 7 bins. We wanted 7 bins. This has 5 bins in it. So let's go ahead and try to customize this a little bit. If you go into the chart, customize, there's a histogram button over here. Okay, and then here it asks you for the bucket size. So that's the bin size. All right. So some of them ask you to specify the number of bins. Other software asks you the bucket size. Here I want a bin size of $5,000. All right. So I'm going to put 5,000 over here. And then it's going to give me, okay, 1, 2, 3, 4, 5, 6, 7. Right. So 1 bin, 2 bins, 3, 4, 5, 6, 7. Okay? Exactly what I wanted. And it's actually also starting at 50,000. Now, does it start at 50,000 for you? Okay, that's great. So that's exactly what we want. If it doesn't start at 50,000, you could go to the horizontal axis and choose the minimum value over here. You set your minimum value to force it to start at that value. Okay? Sometimes you don't have that option, so you're stuck with whatever software the software wants to do. All right? And you're just stuck with that. An alternative option would be to do the frequency distribution yourself and then do a bar graph, but then you're going to have trouble making the bars adjacent to each other. Okay? So how do you make them? Because the first entry for the first frequency is going to be, let's say, 50,000. The second one is going to be at 55. It's not going to put the bars next to each other. So that's why the histogram function is specific and distinct from the bar chart function. Okay? This will be adequate. Whatever it gives you, it will be adequate and it will do the job. Okay? I'll see if I have time. There's another option that we could try, but yeah, that's about it and the limitation with the histogram. Now, Excel has a little bit more options for you to do these histograms. So you could explore that if Google Sheets is not giving you that option, or find an online histogram, but this will do for now. It does the job. All right? Okay. See? So this is what I got. Okay. I'm going to skip this. Selecting a relative frequency histogram. 1 second. Let's see what I wanted to do here. Yeah, so we're just going to skip this one. We're not going to do a relative frequency histogram. So instead of having values, I want to have percentages on the bars. But Google Sheets and Excel, they don't do that. Now in Excel, the way to trick it is to create a bar chart in Excel, and Excel allows you to bring the bars next to each other manually. Google Sheets doesn't allow you to do that. So then it will just be a bar chart of your bin, one of the bin values and the percentage. So don't worry about that. I'm not going to ask you about it. The critical difference between histogram and bar chart, you need to know this, is that in a bar chart, like I said, the bars do not overlap. They don't touch each other. They're not adjacent to each other. In a histogram plot, they are adjacent because it's plotting numerical data that is continuous, okay, quantitative data. All right. Next, we got a heat map, which is any graph that depicts data using color intensity, a color scale where blue is low value, red is high value, green is in the middle. You typically have a color map or a color map that tells you what each color, to what value each color corresponds to. Okay. Now, if you think about it, so we always think about the fourth dimension, like you cannot visualize the fourth dimension and whatever. Well, color is a fourth dimension, right? If you put a infrared gun on something, right, and you see the shape of the thing, you know, it could be a sphere or some object, could be in 3D, but then it has a color on it. So that tells you something about the temperature, right? That's another dimension, or the value of something. Okay. So this heat map shows the percentage of the population who are under 5 years old. Based on this map, if you wanted to start a children's clothing boutique, what area of the country might be the best option and why? Okay, so the first thing you look at is the color map or the color scale. Here, this is telling us this kind of very light blue is for about 4 to 5% of the population is under 5 years old, and then the lighter blue is between 5.8 and 6%, and as you go to the darkest blue, up to about 8% of the population in that region, is under 5 years old. This is really interesting here. You have, you know, this is Texas, right? I know. Okay, and you know, all the way up there, sorry, I don't know all my states. This is Utah. I know Utah and California. Okay, and so California, I was surprised to see California. So I think California is between 6.1 and 6.2%. I was surprised to see that because everybody's bashing on California, or they're not having children, they're all single, right? Well, in fact, they have a good, healthy population, young population, right? Definitely Utah. Now, if you go to the East Coast, right, you see over here a lot, kind of the number of 5-year-olds, less than 5-year-olds kind of shrinks down. Alaska is interesting, right? Florida, nothing in Florida, right? One of the lowest. This is not fertility rate. This is the percentage of the population. So there could be, you know, immigration back and forth between the states, etc. So, all right. So the question is, where would you start a clothing boutique, right? Texas. Yeah, or anywhere in these dark blue states, right? Or just go online now. It's cheaper. Right? Just have a warehouse and ship by Amazon, right? What is it called? Yeah, the fulfilled by Amazon, right? Go on, AliExpress and like pick a product and just fulfill by Amazon, and you have a company. Okay. A line graph, obviously, that's the simplest, like a scatter plot or just a line plot. You have X, Y data, you plot Y versus X. We know how to do this, I hope. And you typically have an x-axis and a y-axis. I don't even have this in the spreadsheet. And you can do a line plot like this. You just simply select the x and y values in your spreadsheet. If you don't know how to do this, come and talk to me or the TAs. It's very simple. You just create a scatter plot or a line plot. Now, you know, if you have taken numerical methods. For those who have taken numerical methods with me, you know I don't like connecting things with a line if you have x, y data and scatter, because when you connect them with a line, you're implying a certain change between two data points, which you don't necessarily know. Okay, so be careful about connecting the dots with lines, right? Until you make a regression analysis, then you can just do a line. Okay. All good. There's a lot of other types of graphs. You'll see every time you watch a study or a news report, they have some really cool graphics to describe a certain statistical result or statistical data. All are okay and good. What I want to discuss next is a few ideas on being a critical thinker when you look at a graph. And it's just looking for trouble in a graph, looking for issues in a graph when you look at something. And I will list a few issues. The first one is the scaling of graphs. And we start by consider the following graph based on US federal minimum hourly wage rates, minimum wage, unadjusted for inflation. So these are just values, no adjustment for inflation. So you're just gonna imagine you're living, no inflation from whatever, from the 60s since they started tracking this, from 1938. Between 1938 and 2009, when the minimum wage reached its current rate of $7.25 an hour, that's unadjusted for inflation. Okay, so people don't make minimum wage is not $7.25, it's probably what, $17, $15 now. But this is unadjusted for inflation. Okay, so for inflation, a rule of thumb, every about 20, if inflation is 3%, the value of your dollar will cut in half every 21 years. So if inflation is 3%, what you buy today for $1, 21 years ago, you could have bought with half a dollar. Okay, that's kind of a rule of thumb. Inflation fluctuates, but on average, over the last century, it's been on average 3%. Okay, so I wouldn't be surprised. Like at 3%, this should have probably tripled now, keeping up with inflation. We'll see. Okay, so now this is the graph when you look at the federal hourly minimum wage and unadjusted for inflation, and you're plotting, you know, every tick mark here is a year of the minimum wage. Now, looking at this, well, great, we are increasing. In fact, we're getting into exponential territory, right? The plot starts kind of nice and linear, but then it starts picking up exponentially. Is there a problem with this graph? Look for trouble. Yes? Yeah. Do you see that? So the tick marks are not equally spaced on the x-axis. You start 1938, 1939, and then you jump 5 years, 6 years here. But yet the distance between these 2 points is the same. It shouldn't, because that distance should have been bigger. It changes the slope, right? So then the growth might be slower or might be larger. Okay? So you have to be careful about scaling your graph. You have to do it truthfully. Don't manipulate data like that. If you do it correctly, this is the picture that you see. Okay? You see a slower rise over here, then sharper rise, then it's kind of steady. Then you see a very sharp rise over here. Then it's not keeping up. This point here, there hasn't been any change since 1980 to what, not a significant change between 1980 and 1990. It was very slow, whereas it should have followed up this exponential rise, right? So this kind of chart displays it now. Between 2005 and 2010, looks like things are being corrected a little bit. Yeah? But scale the graph. That's one of the first things you look at. Sometimes you see pictorial graphs, like people who eat bananas and people who eat apples, and you'll see like they put bananas in a big size and apples in a small size or something. And ask yourself, is this to scale? Is this really to scale? Maybe not. They're trying to kind of inflate the picture. Or they might say not to scale. And that's very important. Okay? If you draw something, sometimes you might have to do something not to scale because you're doing an illustration of an atom and the earth, for example. There's no way I can draw the earth this big and draw an atom, right? I'm going to put under it not to scale, okay, and draw an atom like a small dot and put the earth at this size, because otherwise you can't even draw the atom on the picture. All right, types of graphs. There's uniform, symmetric, skewed to the right, skewed to the left, and multimodal. So it's better to just show you the pictures. This distribution is called symmetric. It's a symmetric plot, a symmetric graph. Forget the name, normal distribution. We will learn about the normal distribution later. But this kind of graph is symmetric. There's no preference on either side. The peaks are a little off. They're not equal, but that's fine. It's within statistical error, right? But the graph is symmetric. A graph that's skewed to the left, it means it has an outlier on the left. What's an outlier? Is one data point that is so far away from all the other data points. Okay? Do we have an outlier in this class based on height? Okay, we do have an outlier, your TA, right? So, thank you, Zach. I chose you. You're perfect for statistics, right? So everybody is kind of clustered on one range, and then there's an outlier, right? So that's an outlier. It's just a few data points that are outside the range of the data. So when you look here, most of the data is clustered around this range, but then there's a few way out here. You see this sometimes in salaries. We'll give an example in the next chapter. Most people are doing 80, 50, 90, 70,000. Then CEO making 500,000. That's an outlier. Now, do you include the outlier on the data or not? We're going to study this because the outliers will skew your data, will skew your averages significantly. Okay. In fact, there was a story. I was going to tell that when we study the mean, but I'll tell it now. So the geography department, I forgot the university, I think. Some university in the US, I forgot the name. So they reported that on average, their geography students are making like $200,000 versus the national average, excluding that university, national average, everyone else making like $80,000 for geography. Turns out they had one outlier, Michael Jordan, in their data, who got a geography degree, but then went on to be a basketball star, and his salary was like $1,000 million a year, right? It skewed up all the statistics, right? So that's an outlier. Maybe you should exclude the outlier in that case, right? Because it's gonna really skew the data, or report a different number. Same thing when there's an outlier on the right, then we say that the chart is skewed to the right, okay? Now, when there's not much change in between the points, you say that this is a uniform distribution. The chart is uniform. All the data just have about the same value. Now, to whet your beak as we start planning for the next chapter, you're going to see distributions that have 2 peaks or 3 peaks, okay? We will refer to the peaks as the modes of the distribution. So that first one is a unimodal distribution. That's a unimodal distribution. That's a unimodal distribution. It has one mode, okay, which is a maximum value. This has 2 modes, bimodal distribution. This has 3 modes, multimodal or trimodal distribution. Okay? Yes? It has no mode. Good question. A uniform distribution has no mode. We will study mode in the next chapter. Let's take 5 and begin on the next chapter, okay? Sorry, Zach. Thank you for participating. You're like I swear I didn't plan for this. It's just like on the fly. I'm an outlier. I'm the only bald person in this classroom. Okay. So how is the course so far? Boring or slow?
It seems a little slow.
Well paced.
But that's probably like because I've already learned.
You've already taken this, yeah. Yeah. Okay, yeah. Well, it's gonna get very hard very quickly, right? But kind of building up these concepts and easing into them, I think is appropriate. I don't want to waste a lot of time on these introductory chapters, so yeah. Also can't go faster because I don't have material. So yeah, next week we'll start probability for sure. Yeah, it's gonna be a tough one.
That's when like the math will start.
Yeah, that's where, and kind of complexity. So I think I'll do exam 1 on this part, exam 2 on probability, and then the final. But I don't know, because there's a lot of statistical inference stuff at the end.
Yeah.
I'm not sure.
Yeah.
Maybe I'll wait a little bit for probability and do an exam combining this stuff plus some probability to exam 1.
Yeah, I remember last year it was like over half the class was probably the inference part.
Half of it was inference,
Yeah.
yeah. Because you guys started with Zangle, you took it with Zangle, right?
Yeah, we started
You started
probability
probability.
second
Lecture, yeah. No, I think this is, I think this is, we'll see
I
at
think
the
this
end.
is better. I think Zangle
Yeah.
was a little too fast.
I think they were too ambitious with the material. I remember like students were, I don't know, we'll see. And they took it in the fall, so they were not as ready possibly. Okay. Let's resume. The next chapter, and you'll see I'm going chapter by chapter. I'm following the textbook. We'll see where this lands us. But this is the last chapter of the easy stuff, of the descriptive statistics. That's it. There's nothing more you can do with descriptive statistics beyond this chapter. And then we will hit probability. But this is where we start seeing some more math. Still, it's lightweight. Not too advanced, but it will make you think a little bit. So if you think about it, we're still within descriptive statistics. We have data, we're describing the data. We looked at visual descriptions of those data with the graphs, Pareto, pie charts, etc. Next, we're gonna start reporting numerical descriptions of those data. I tried to put some learning objectives here. There's probably a few more. We'll see if we cover those. But so far, by the end of this chapter, you'll be able to define, calculate what we call measures of center. Those are the mean, median, and mode. Sometimes you will not see the mode described in descriptive statistics because typically the mode is applied to nominal data, not quantitative data. It's not super important for quantitative data, but I like to just include it. Identify which measure of center is appropriate for a given data set. So if it's quantitative, you choose mean or median, and then which one of those is better, mean or the median. And then if it's qualitative data, you'll pick the mode. Estimate the mean value for a frequency distribution rather than the original data. You'll see it's easy to compute the mean value from the original data. You just take all the data and you average it. But what if I give you data that's already grouped into bins? You see, bin 1 is 3 people, bin 2, 6 people. Can you compute an average from those data if you don't have access to the original data? There's a trick to do that. Define and calculate what we call measures of spread or dispersion, how far away the data is from the mean. If you remember, if you took numerical methods with me, you remember we spent quite a bit of time talking about this in regression when we treated the mean as a model to represent the data, and we talked about the dispersion with the standard deviation as being the error with respect to that. So we're going to revisit this concept here, and we will keep revisiting it as we build into probability theory. Define, and so we will do also the same for group data or data that frequency distributions. Define and compute quartiles and identify outliers in data, a more quantitative measure of outliers. So we'll start with measures of center, and the first one is going to be the mean or the average. It is the simplest statistic or parameter one can report. In numerical methods, that's the question I ask you. If I give you a bunch of data and I tell you what is the simplest number you can report on those data. So say you want to estimate your budget for next month for food. Well, you look at the last 6 months of your credit card bill, see how much you spent on groceries or on dining out. You take the average of those and say, okay, that's going to be roughly what I expect to spend next month, right? So the average is really one of the simplest measures that you can use to report a summary of the data. We're going to distinguish between sample and population quantities because those will have different symbols and different properties, okay? So remember, a property, a number related to the sample is called a statistic. A number related to the population is called a parameter. Okay, so we need to distinguish those. The first formula is simple formula for the sample mean. If you're given data, x1, x2, x3, or xn, a bunch of numbers, okay, n of those, then the average is simply their sum divided by the number of entries, and we call that x bar typically. A summation of all of those values over the number of data points, okay? Now we will refer to x bar as the sample mean. For the population mean, we will refer, so x bar is a statistic, it's a sample mean. For the population, the mean value is reported as mu. That is the standard symbol used for a population mean value or a population average value. It's a parameter, it's a property of the population. So similarly, that population mean is computed the same way as the sum of all the people or the subjects in the population divided by the total number of people in the subjects in the population. Okay, and you define your population. My population could be this class. Doesn't have to be the entire world. Okay, it's you define what your population is, right? Most of the time, you cannot measure that in the population, so you have to infer it. So after this chapter and moving forward, we will want to compute a sample mean and figure out how we can predict the population mean. We will compute a sample standard deviation or measure of spread and try to predict how much the spread or infer how much it is on the population. That's what inferential statistics is. Okay. There's a little rounding rule. I don't pay much attention to that, but you know, if you want to, you typically round to one more decimal place than the largest number of decimal places in the data. Typically, your data all should share the same number of decimal points. Let's say 4 decimal points. You can compute the mean, add one more decimal point in your data. It's just good practice in statistics. So we start with a simple example. Students were surveyed to find out the number of hours they sleep per night during the semester. 0 hours, right? Here is a sample of their self-reported responses. 5, 6 hours, 8 hours, 10 hours, dude. Like 4, 6, and then 9. Okay, so you can compute the mean in your calculator. You can use the average, or you can do this in Google Sheets. Either way, if you do it in Google Sheets, we're going to get a chance to do that later. The function is called mean or average. So you do this, you sum them all up, you divide by the number of entries in the sample, gives you about 7 hours. These students in the sample, on average, they sleep 7 hours. Okay, so now you might be laughing like this, the mean is such a simple concept, like even my 7-year-old now can understand the concept of the mean, like how much do we spend at the arcade, Dad, when every time we go, I'm like, don't talk to me about how much we spend at the arcade. I have to sell a kidney every time we go to the arcade. They have this really cool and stupid Minecraft Dungeons arcade. It is so addictive, right? So anyway, I'm actually, for the game nerds, stay in class after. I'm building a Raspberry Pi to connect it to my arcade at home, so we can talk about that. But these concepts were not familiar to people 200 years ago, 300 years ago. Okay? The idea of the mean value. Maybe some mathematicians knew that, right? But it wasn't a common concept like the average. Maybe people had a feeling of it. In fact, there's this story. He's called the knower of the secret of the dice. And so an ancient Indian story recounts of how King Tuparna, I think that's how it's pronounced, or Tuparna, known to be a frequent gambler. So gambling is as old as humans learned to walk, right? Estimated the number of leaves and fruit on 2 large branches of a tree, okay? And that's important because people, agriculture was a big deal. So estimating which tree to pick and which is more dense was a very important skill. And his secret was that he only used the leaves and fruit of a single twig as the average. So he went and picked a single twig from that tree, okay, and measured the fruits and leaves on it, and assumed that on average, every twig on those branches is going to have that same value. And then he estimated the number of twigs on each branch and did the multiplication, and he was within striking distance. And then his estimation turned out to be very close to the actual value. When asked how he was able to do this, he replied, "Know that I am a knower of the secret of the dice, and therefore I'm adept in the art of enumeration." They called it enumeration, okay? So, this was a big deal. Like, you would be a magician if you go back 500 years and, start reporting fancy numbers and predictions with mean values, etc. So we take these for granted, but it took a while for civilization to figure these ideas out, okay? All right, here's another example. Rutherford downloaded 5 new songs from Apple Music, not a torrent or Napster, right? He downloaded them fair and square. He knows that on average, the songs cost $1.23, okay? And if 4 of the songs cost I feel like I'm in high school question here, okay? But still, it's going to be useful for later when we talk about variance and degrees of freedom. If 4 of the songs cost $1.29 each, what was the price of the 5th song that he downloaded? So the average value. The cost of 4 of the songs. You're asked to find the price of the last song. Okay. The reason I gave this example is because if you know the mean, you don't have to know. You only need to know n-1 data points, because the last data point you can always deduce it from the mean. It's very simple. The mean I put mu here. It should be x bar really. Unless the population is his 5 songs. But let's say, actually this is mu because the population is 1.29, 1.23 on average. So we know the mean value, and we have this sample, 1, 2, 3, 4, 5, right? We don't know x5, which is the cost of the last song. We know all the other songs, they cost 129. There's 5 of them, and the mean is 123. Then from that, we can deduce one of the values. So the point here is to say that if you know the average, you only need n-1 data points to deduce the last data point, right? Because there's always, they're dependent on each other, okay? And you can use that to your benefit. Now, we can upgrade the mean with a weight. Why, do you ask? Well, when you're calculating your grades, your final grade for the course, you had 90 on the exams, 80 on the homework, right? 100 on the quizzes. But 90 on the exams only constitute 35% of the grade, right? And homework is only 25%. So you have to weigh each value by its corresponding percentage to compute the final and total value. Okay, so we call that a weighted average. And you upgrade that summation with each value in the data. You multiply it by its corresponding weight. Now, the weights are given to you usually, or they're determined from the setup you're dealing with. You will know what the weights are. But then divide by the weights, by the summation of the weights. Okay? Summation of the weights. Now, this is very important because it's not always true that the sum of the weights is going to be 1. Okay? We'll see an example of that in a little bit. All right? So this is a more general formula for computing the average. Okay? Previously, the weights were 1. So you had summation of xi over summation of 1 n times. So that will give you n. So you get summation of xi over n. So this is a more general formula for the sample mean, or for the mean value. Okay. So the syllabus in Walter's US History class states that the final grade is determined by tests, 40% on the tests, 20% homework, 10% on quizzes, and a final exam, 30%. Wow. Okay. So Walter wants to calculate his final grade in the course, and this is these are his average grade in each category. So you have on tests, his average is 83. On homework, his average is 98. Quizzes is 90, and final exam is 87. Okay, and then we know the percentages for each one of those categories. Okay. So we can do this let's do it in Keynote, and not in Keynote, in Google Sheets. Okay, so let's do this in Google Sheets. Let me see, open up a new sheet. See if I can do this. All right. So let's create a new sheet. Make a new spreadsheet, and we'll call it Chapter 3. Chapter 3 in class. Oops. In class. Okay. So what I have here are tests. Let's also make this a little bit bigger. 50%. We got tests, homework, quizzes, final, and then the total value. And the weights are 40% for the tests, and was 20% for the homework, and then 10% for the quizzes, and the final was 30%. They should all sum up to 100%, and that's true. You can change you can format the data here and make it percentage. So you can go and say number, oops, percent, and you'll get that. Okay? Let me see. Oops. Yep. Okay. So next are his grades. So I'm going to create one more row at the top. Okay. Weights and grade. Okay, so he had 83 on this one, and then 98 on homework. Good job, Walter. 90 on quizzes, and 87 on the final. Okay. Now the formula for so this is the average grade in each category. Okay. We're not going to average them and divide to get the final grade. We can't just average them and divide them by the number of, category by 4. So tasks, homework, quizzes, and final, right? Because each category has a different weight, right? So instead, we need to weight the grades first by their relative percentage, and then do the average. Okay. So we can do here weighted grade. Okay, so we have 8. Oh, look at that. It automatically knew what I want to do. I want to multiply 83 by 40, or this C2 by B2. Okay, and if I just press enter, it does that for me. And you can drag these all the way down. So now you get the weighted grade out of the total percentage. Okay, now finally what you want to do here is sum this up. So it's the summation, but you also need to divide by the weights, which is this number over here, right? But it is 1 already, which is fine. So, but don't forget to divide by the weights, because there's a trick question that I will ask next, where if you don't divide by the weight, you get the wrong answer, because the weights are not going to sum up to 1. Here they did sum up to 1, okay, which is fine. The denominator is fine. So you get his his final grade is 87.9, 88. And apparently what you can do with these tables here, so it gave me the option the other day to convert this to a table. Anyway, you can convert this to a table, it would look a little nicer. Okay. Let's see. right? So this would be the formula that you're doing. You're weighting each grade, or the way I like to think of it is that where you're taking the average of category averages, the weighted average of category averages. Each category has an average, but the importance of each category is different. Tests have 40% importance out of the rest of the other ones, right? So you're weighing those averages accordingly and then adding them all together. And then that gives you the weighted average. Okay, now this is the trick question. Not a trick question, but you have to be careful about the dividing by the weights. Let me see. Actually, no, not in this question, in another question. Now let's consider what would happen if Walter had the same grades, but the percentages for some categories were different. How would his grade change if now the homework counted for 30% and the final exam was only 20%? Okay, so we're going to switch things up. We're now going to do homework 30 and final exam 20. Okay, so all you have to do is come here. Homework is going to be 30, so I'm going to put 0.3. And final is going to be 20, so 0.2. Oops, oh, I'm going to put, 30 and 20%. Okay, his grade is going to be 89. Okay, his grade is going to be 89. All right, so not that much of it, not that big of a change, right? Not that big of a change. Although you think that there's a dramatic change going from 20% from homework to 30%. That's a big change, almost 50% more. Dropping the exam from 30 to 20%, that's a 33% drop in weight. But his grades were good on those. It didn't make a big difference, right? So what did he have? He had 90 and 87, right? He had 98 on homework and 87 on the final. So he had high grades on those, so it didn't make a big impact on him, right? Okay. Okay, this one is interesting. This is where the summation of the weights is going to show up. Another example, at the end of the semester, these are simple examples, I know, okay? They're simple and easy. Do you have a question? Oh, okay. Let's just do them, okay? We'll see the boredom level is gonna change next week with probability. Okay. At the end of the semester, Heather knows all of her grades in her sculpting class. Anyone taking a sculpting class here? Underwater basket weaving, okay, good. You're doing good engineering degrees. Okay, her sculpting class except for the final exam. Here's a breakdown of her points and how much each category counts toward the final course grade. So on tests, they count 35%, that's the weight, and her average grade on tests 78, so class assignments 20%. She got 92 there. Semester project, 93 she has, counts as 35%. And the final exam only counts for 10% of the grade. So now the question is, calculate the weighted mean for the portion of the grade that she has completed. Okay, only the portion of the grade that she has completed. Okay, so she's completed tests, assignments, and semester project. The weights add up only to 90%. Okay, so you have to make sure that you're only adding the weights in the denominator to 90% or 0.9. So make sure you don't miss that. Okay, so similar to the previous example, we do this. We have the grade 78 and 35% for the tests and whatever the class project, etc. And you divide by the weights for those categories. So notice the weights here, they sum up to 0.9 because they're still the final exam that we didn't include. So don't forget to divide by the summation of the weights for however many categories you're dealing with. Those weights are not going to, it's not until you get everything together that the weights will sum up to 100% usually, okay? So Heather has 87 for her sculpting grade so far without the final exam. Okay, so now we know that the weights are the percentages for each category, etc. And the values X are the scores for each category. However, now It is not the weighted mean that we don't know, but the value x for the of the final exam grade. Use the same formula as the same one used in A, but add the final exam category with a weight of 0.1 and the unknown value, okay, and solve for the, so yeah, so this is the second question here. What grade must Heather make on her final exam to have a final grade of 90%? Okay, so we want her final grade to be 90%. Okay, can she do it? Which would be the A that she desires. Assume that the final exam is worth 100 points. Okay, assume that the final exam is worth 100 points. So now we follow the same procedure, except now we don't know the value for the grade on the final, X final. Okay, we don't know X final. Okay, and we have her expected value for the final grade should be what she wants 90%. What is X final? Turns out she has to get 17.5 on the final exam. So unless there was a bonus on the final, like Professor Saad usually does, right, there's no way she can get an A. Okay, because you cannot have more than 100 points. Okay? So now you can do this in Canvas actually. You can, there's a page in Canvas for your grade. You can go and start playing around with the final exam grade to see what grade you need to get. But now you understand the mechanics behind it. Okay? So it's mathematically impossible to get more than 100. Now the highest final grade she could achieve in this class is 88.25. So in other words, she got 100 on the final. That's the maximum grade she could achieve on the final. What would be her grade? Only 88.25. That's not much difference from her current grade, which is 87. Why? Because the weight on the final is so small, only 10% of the total grade. So there's not much she can do to increase her grade. Okay? All right. Now finally, question C. So let me go back and look at the questions. What grade must Heather make on her final exam to have a final grade of 80%, which would give her a B for the course? So remember, her current grade is 87%. So she's beyond the B. But like, you know what? I'm not going to study for the final. I'm just happy getting an 80%. Okay? And so, you know, what is the what problem she needs to solve? What one problem she needs to solve on the final exam that has so many points to guarantee her a B? So again, we use the same formula, but this case we're changing the average. We put the average at 80. What is the final exam grade she gets? 17.5. So, you know, problem 1 and question 1 on problem 2, get 17.5, get a B, and move on with life. Okay? So that's what she wants to do. Okay, great. I don't recommend that approach. It's not your grades. Don't treat your grades and courses as transactions. And if I do this, I do that. You know, just immerse yourself in the course and do well from the beginning. You don't know what's going to happen by the end of the semester. Okay. Now, what about data that's given as a frequency distribution? Now, frequency distributions, they also sometimes call them grouped data because you group the data into bins and classes and categories, as if we need one more definition, right? So let's just call them frequency distributions. Remember the salary data that I showed you for the highest early career salaries with bachelor's degree. We had a bunch of data. We had 25 data points here. Now, if you compute the mean value of this sample, it's $67,468. But what if you did not have access to those data? What if I only gave you these? The classes, the bins, and the count in the bins. Could you somehow estimate the mean value? Give me some ideas. Go ahead. Okay, so you do what? You do what?
So, for example, the first bin, you just find the center of those numbers below numbers, and then multiply that by 3.
Okay, that gives you the weighted. Okay.
Yes.
What do you think? Thumbs up. Okay. Now, in statistics, I always said in numerical methods is not a democracy. In statistics, there's like opinions. There could be opinions, right? But this question is not a democratic question. Yes, go ahead. Here? Above and below. That's a great insight. Yes, so a ballpark number is going to be there. Okay, but not all data are going to present themselves that way, that nicely. They might be uniformly distributed, or they might be all skewed to one point. But still, how can I get to a numerical value of that, right? So if you remember in the previous examples, I said what you're doing with the weighted mean, you're taking the average of each category, and multiplying it by a weight to compute the total mean. If you consider these as categories, we know the weight for each category, we just don't know the mean for each category. What's a good guess for the mean of a category? Like as your colleague said, just get the center point. The center point, as far as I know, there's 3 people in this category. On average, the 3 of them are making about $52,500. Okay? They might all be clustered closer to the edge here or closer to the lower side, but it's still a good estimate because we bin them all in that category. If your category is smaller, your estimate is going to be accurate. But that's a good strategy when you have loss of data, loss of information. Just take the average of each category, or the midpoint, which is the midpoint. Take the midpoint of each category and weigh it by the count. And then you can get an estimate of the mean value for frequency distributions. Okay. So that's the strategy. Now, the mean for each bin, we're going to estimate the mean value for each bin by the center point. Take the upper limit minus the lower limit and divide it by 2. Very simple. Okay. Why? Because that's the best guess we can get in the absence of any other information. How the people are distributed inside the bin, we don't know. As far as we know, they all in the middle. Okay, so we just take the midpoint, and then the formula of the mean would be x bar, which is x bin, the first bin, the mean value of the first bin times the count in the first bin plus x bar, the mean value of the second bin times f2, etc. You still have to divide by all the weights, okay, by the summation of the weights, but that will give you the right value, okay, a close value. So estimated mean is 67,499. The true mean is 67,468. Pretty darn close, okay? We lost a lot of information when we went from the full data to the frequency distribution, okay? We lost a lot. But we still were able to extract that information reasonably well, okay? The next measure of center is the median. The median, think about, when you think median, you think middle value. Median, by definition, is the point that splits the data in the middle. Half of the data are below the median and half of the data are above the median. So when you hear that the median house price in Salt Lake City is $400,000, it means half the homes in Salt Lake City are less than or equal to $400,000 and half the homes are greater than or equal to that. Okay? That's the median. The way you do it, you list the data in ascending or descending order, whichever you like. If the number of data points is odd, then you pick the center point. So if you have 5 data points, is the data point number 3 is going to be your median. If you have an even number of data points, you get the 2 values in the middle and you take their average. Okay? Very simple. Now, obviously, this is easily done on a few numbers. We're going to do it in Google Sheets eventually. And so we start with this example. You have unordered data, an odd number, 3, 4, 6, 3, 4, 5, 7. So we have an odd number of points, 7 and 8 points. Okay, so we put the data in the correct order, 2, 3, 4, 6, 7, 8, 9. 6 is right in the middle. excuse me, that is going to be the median, okay? Now, for the other data points, we have 1, 4, 5, 7, 8, 8, 9, 9. Okay, so what is the middle? We have 1, 2, 3, 4. The midpoints, 7 and 8. You take 7 plus 8 over 2. The median is going to be 7.5. All right? Okay. You can do this in Google Sheets and Excel. We'll get to do that. Once we do an analysis on all three properties for one data set. Now, why is the median important? Why is the median important compared to the mean value? Okay. Think about the Michael Jordan example. Yeah, Nicholas.
It mitigates outliers.
Yeah, it does. It does mitigate outliers. It's not affected by outliers because it's not affected by the numerical value or the magnitude of any outlier. It only works by the number of data points, strictly by the count of data points. And we say that the median is not affected by outliers. Okay, the median is not affected by outliers. Here's another example. A small company employs 4 engineers who each earn $80,000, and the owner, also an engineer, gets $200,000. Okay? So one could advertise and say, the average salary at this company, you know how to compute the average, it's 800,000 times 4 employees, plus 200,000 over the total of 5 employees. So this is what you get, the mean salary for this population, 4 times 80,000, so 4 employees each making 80,000, plus the boss over 5. So on average, they make $104,000 at that company. But is that a true figure to report? What if he made 500,000, right? Does that mean that the average employee at the company makes $200,000? That's not true. So in this case, the median is a more appropriate measure to report. And the median here is actually $80,000. It says half the population makes 80 and the other half makes less than 80 and the other half makes more than 80. Okay? Now I have to ask this. What do you think about working for this company? I'll see you next Tuesday. Okay? Godspeed.